Now I want to have a bit closer look at the effect of cavitation. That's a really important effect, and you have to know what it is if you deal with fluid flow. And normally I teach you something about gas flows or about liquid flows, but and you know Bernoulli's law, for example, you can use it for gas or you can use it for water or for oil. You can use it for every laws, but from time to time there are some special effects for the fluids that you don't have at other conditions. Yeah? Let me explain. For example, if you have a gas flow, a flow of hot air, you will never get any gravitational effects. But if you have a water flow or a liquid flow, and you get regions where velocity is so high that the static pressure have to go beneath or under the value of 0. And you know this is physically not possible. You can't get negative pressures, they do not exist. If you have a gas, you will get a vacuum, but if you have a liquid, you can't get a vacuum in liquid. So something has to happen, some additional effect has to happen. And if you have a pipe system and you make your energy balance and calculate Bernoulli's law, you can get regions where you get negative pressures, but they're not physical, they're only mathematical, it's only a calculation, but it's not a real physical effect. So something has to happen there, and this is the so-called effect of cavitation. If a pressure in a liquid goes below the saturation pressure, and saturation pressure is really small, it's only 2100, about 2100 pascals for water, and that's a really low value. And if the pressures, the static pressures goes beneath this 2100, then you will get bubbles. And bubbles are like holes, like cavitations in the fluid. Cave, cave, like a cave in the fluid. Let's explain it like this. And you will get gas, and this will, this will of course influence the fluid flow, and it will influence the looses in the pipe, and it will affect really hard the walls of the fluid. If a cavitation bubble hits the wall, it will implode at this position, and it will cause really high tensions, really high temperatures, and you can destroy even metal walls and or pumps. We know this problem really is a really serious problem for pumps, for example. Here I explained it a bit in a diagram. Maybe you all know the effect of boiling in water. If you cook your spaghettis, you heat the water up to 100 degrees at 1 bar, that's our surrounding pressure. Then bubbles will start to boil, they will appear, and they but on the other side you can also produce these bubbles if you lower the pressure. If you can imagine, you should cook your spaghettis in high altitude where you have low pressure, the bubbles will appear really faster. And that's directly an effect that was discovered from scientists when they wanted to climb up the Kilimanjaro and they wanted to cook the potatoes. They discovered that at these high altitudes the water will boil much earlier. It will not reach the 100 degree, and they were not able to boil their potatoes. Or for example, when the British pioneers wanted to measure the altitude in the Kilimanjaro in Tibet, at the Himalaya region. Then they always cook tea, and they measured the temperature, the cooking temperature of the tea, and they discovered that at different altitude the cooking temperature changed, and so they were able to measure the height in a really precise way. Okay. So, and you can have hard and soft cavitation. Hard cavitation means you can get cavitation from the liquid itself. For example, if you have water and you get bubbles, and the bubbles are made of water steam, then this is hard cavitation. Or if you have oil or a gasoline and you have cavitation in this, for example, diesel oil, and the bubbles are made of diesel steam, of oil steam, this means hard cavitation. But you can have also another more easy way of cavitation, so-called soft cavitation. And soft cavitation is if the gas is not the gas of the host liquid. It is a gas. It's another gas. For example, you all know this. If you have sparkling or mineral water, if you open the bottle, the bubbles appear, and these bubbles are not water steam bubbles. These bubbles are carbon dioxide bubbles. So you have another substance, for example, carbon dioxide, solved in the water, and now if you lower the pressure, they will form bubbles, and these bubbles will be formed more easy than the hard cavitation bubbles. Soft cavitation bubbles, it can be also oxygen. If oxygen, or for example air, if you have gasoline or if you have diesel, there is always some air or some water mixed in this diesel. And now if you have a cavitational effect, you can get water steam or oxygen bubbles inside the diesel fuel. And okay, so we also know a cavitation number. It is formulated, and we use this cavitational number to calculate cavitational effects. And I explained you, cavitation always appears if you go lower than the saturation pressure of the dissolved substances in the liquid. And so we formulate the cavitation number if we have the pressure, it has the vapor pressure, and we divide it by the dynamic pressure. Here are some pictures of cavitation in technology. I explained you cavitation is really serious problems in pumps. It will destroy pressure pumps, and we often have this effect, for example, in diesel or gasoline cars, that the cavitation destroys our pump. Or, for example, we have this effect at ships. Here we have you can see also ship screw from a ship, and you can see the bubbles here that are produced at the blades of this screw, and you can also see here really dangerous erosion effects, because the bubbles, when they implode again, so the erosion effects are not they do not appear when you produce the bubbles. This is not dangerous, the production of the bubbles, but the erosion will appear when they implode again with a high temperature and really high. They can get thousands of degrees centigrade, or they can get really high noises or high pressure waves, and then they destroy even metal. And it can happen that you destroy your screw of the ship if you once drive over the Atlantic Ocean, and then it's damaged afterwards if the design of the plate is not in a good way. So designing this plate is a really important topic of computational fluid dynamics to build it to prevent cavitational effects. And we don't even have to look at technology, we can also look at the nature. And there's one small cancer, one small animal, and he can also use the effect of cavitation. He can produce high cavitation bubbles with his scissors, with his hands, and it's a pistol cancer. And this pistol cancer, he have one big hand and one small hand, and he can produce these bubbles with his hand, and he can shoot on animals, and he can shoot on smaller enemies, and he can destroy them with his cavitational bubbles. And now you ask me, how can he produce cavitational bubbles? He's not made of metal, he has only a small body, small hands. That's a secret of nature. It's not really discovered how the pistol cancer can produce this cavitational bubbles, but he can do it. He can use these effects. Okay, here's also some positions in pipes, and I taught you that cavitation is really dangerous for pipe systems or for any kind of armatures. And here are some special positions, and it will always act there where you have high pressure drops. So, for example, here you have this Venturi pipe system, and in this narrow region you can have pressure drops, or in the elbow, after the elbow region, where you also produce turbulence, or after throttling position, or in the edges of sharp edges. So you always have to prevent sharp edges. You have to, if you build up a pipe system, you have to use round edges to prevent cavitational effects. And here's a small sketch about how the erosion and the damage acts on the wall. If you, for example, have a bubble, and the bubble gets a so-called protrusion, it will build also a cave, it will bend the surface, and then you will get like a sting, like a short sting, and the bubble implodes, it hits the wall, and that's also something maybe I have to explain. The bubbles always try to get to the walls. Yeah? Maybe if you look at your glass of Coca-Cola, or if you look at the bottle with mineral water, you see the bubbles will always like to go to the walls, because they have less energy, and the bubbles need a lot of energy to build up their surrounding surface, and if they can touch the walls, they will need less energy. So they always try to save energy to go to the walls, to touch the walls, but when they go there too fast, they can implode, and then they hit the walls, and they damage with this pressure, with this high pressures, high temperatures, they damage the walls. And you can see this really characteristic damages. It looks like them wormholes. You can, if you once have seen it, you can really good characterize erosions. For example, here that's a pump impeller, and you see the pump impeller, this design was not really good. You see the plates, and the plates are really like worms have eaten the plate, like they bite pieces out of the metal. And this is really characteristic for corrosion based on cavitation. And what can you do? You can make the geometry a bit different. You can change the geometry in this blade region where cavitation acts, and then you have the possibility. It's always better if the implosion will happen after the fluid exits the pump, or if the implosion acts in the free flow fluid, not at the walls. And there you can change the design a bit to force the implosion in the free flowing fluid region. Okay. Or you can also build some walls that you do not need, that are thick enough and where you do not care about the cavitation. Maybe one thing I have to tell you, you can hear this cavitation effect. It's a really loud sound, and it's like a crying sound. And if you have a nozzle or if you have a pump and it starts to cry, it's like a sound of like a really high noise. Then you can see it's highly cavitated in the pump. Okay, yeah, here's also some sketches of a diesel injector and a nozzle tip. And there's the same, if you have a high cavitation region inside your nozzle, it will start to sound like a crying of the